Hi, my name is Daniel Kalny, and in my presentation I'm going to show what would a green erase chip reply if asked, "Can you speak USB-ish?" Almost everybody knows what USB is, Universal Serial Bus. Although there are some people who believe it's a kind of vehicle, it's generally known as a means of connecting peripherals to computers. But how does USB work? As users, we usually don't need to know. However, my intention to implement a USB host in GA144 chip forced me to study USB in some detail. For those who are not acquainted with USB internals, I'll start this presentation with a 10-minute course on USB. A complete description of the bus is given in a USB specification. There is also a lot of literature on this subject. However, I consider as the best starting point a tutorial named USB Made Simple. The introduction to the USB that follows is an abbreviated version of this tutorial. USB is based on tier-start topology. There is only one host, one or more hubs that provide forking of the bus, and a number of devices. Cables have 4 wires, 2 data lines, power and ground. There are several connector types nowadays, but here we are concerned with a Type A plug which is found on such devices as mouse or keyboard. The communication is half duplex. Thus, only the host or one device can talk at a time. Communication uses differential signaling on D+ and D- lines. USB device can also be powered from 5-volt V-bus, in which case a current limitation applies. Both D+ and D- lines are pulled down at the host side with two 15K resistors. There are different data speeds, the original ones are shown in the table. A device communicates its data speed to the host with a pull-up resistor connected to either D+ or D- line. The line can be present in either detached state, when no device is connected to the host, or attached state. When a low-speed device is attached, D- line goes high due to its pull-up resistor, and the line is said to be idle. We can also talk of bus states. On two data lines, we can recognize 4 basic states: J, K, single-ended 0, and never used single-ended 1 state. The polarity of D+ and D- lines in J and K states is shown for low-speed bus. It is reversed in full and high-speed buses. Another state is reset. The bus is said to be in reset state whenever there is a single-ended 0 during more than 10 milliseconds. To end transmission of bits, host or device appends single-ended 0 for 2 bits time, followed by 1 bit of J state, and then let the bus go idle. This signal is called end of packet. When a low-speed host sends end of packet signal on an otherwise idle bus, we call it keep alive signal. This signal is used in order to prevent the device to enter suspended state, which happens when line is idle for more than 3 milliseconds. Every device on the bus has an address. Address is 7 bits wide, with range from 0 to 127. Address 0 is reserved for uninitialized devices only. Each device has one or more endpoints. There may be up to 16 endpoints per device. Endpoints are one-way ports sending data either to the host or receiving data from the host. Only endpoint 0 communicates in both directions, and this endpoint is used for configuration of the device. Bytes are always transferred least significant bit first, and for multi-byte data, least significant byte is transferred first. Data are encoded using non-return to zero inverted encoding scheme. Thus, for 0 bit, polarity of data lines is changed, while for 1 bit, there is no change in polarity. In order to avoid long periods of unchanged polarity when transferring a sequence of 1 bits, after 6 consecutive 1 bits, there's an automatic insertion of a 0 bit. This is called bit stuffing. Packets are the smallest transmission elements. They are composed of integer number of bytes. Before and after a packet, the bus is held in the idle state. Every packet has the following structure. It starts with a sync pattern, which is made of alternating J and K states, except for the last two K states. Translated to bit value, sync is made of 7 0 bits, followed by a single 1 bit. Since data are transferred least significant bit first, sync pattern is actually 80 hex. As we've already seen, end of packet is made of two single-ended 0 states and one J state. Between sync byte and end of packet there are data bytes. The first byte is always packet identifier. As the name suggests, PID is used to identify type of the packet with its four least significant bits. Upper four bits are inversion of the lower bits as a fast error check. Let's have a look at the different packets. First we have a token packet. This packet is always the first packet in a transaction. It indicates device address, endpoint and purpose of transaction. In low-speed USB we have in packet, out packet and setup packet. Then we have a data packet. It is used whenever we need to transfer some data. The payload may be 0 up to 8 bytes long. Error check is based on CRC16, which is appended to the payload. If more bytes need to be transferred, they have to be split in several data packets. Data packets are identified with either data 0 or data 1 PID. Finally, we use handshake packets. Those packets are used to confirm status of transaction. It's a simple means of providing handshake between host and device. Successful transactions are confirmed with an acknowledge packet, while transactions that cannot be finished, for instance due to the device being still busy, are handshaked with a negative acknowledge. Keep in mind that when there is an error in transferred data, no handshake is issued, and as a consequence of timeout, the sending side tries to retransmit the data. Stall handshake informs the host that the device has encountered an error that it cannot repair on its own. One layer up, the USB communication is made of transactions. Transactions are sequences of three packets. They provide a secure transfer of data. We recognize three transaction types. Out transactions, where data is transferred from the host to a device. Alternating data 0 and data 1 packet identifiers are used to check for lost packets. In the out transaction, host sends token and data packets and expects to receive a handshake packet from the device. In transaction is similarly used for transfer of data from a device to the host. Again, data 0 and data 1 alternating PIDs are used. In this transaction, the host sends a token packet, device sends a data packet, and the host confirms with a handshake packet. Finally, we recognize a setup transaction. It is similar to out transaction, but payload is always 8 bytes long, and only data 0 packet identifier is used. On the highest level, the USB protocol is made of different kinds of transfers. In low-speed USB, we use only two of them: control transfer, used for initialization and configuration of a device, such as assigning its address and selecting the appropriate configuration. Communication takes always place with endpoint 0 in both directions. The second transfer type available in low-speed USB is interrupt transfer. It uses in or out transactions, though in transaction is more common. The transfer is used for low throughput communication, often in regular intervals, such as in communication with a mouse or a keyboard. Finally, we need to mention a process called enumeration. When a device is attached to the bus for the first time, the host starts to request descriptors from the device. Descriptor is a data structure providing host with information about the particular device, such as the maximum data packet length. There are many different types of descriptors. When the host gathers the necessary information from descriptors, it assigns an address to the device, configures the device as appropriate, and can start data transfer as needed. There is a distinct type of devices called human interface devices. These devices can provide additional HID class descriptors, which among other things describe reports. This is, in what format the device communicates data to the host. Apart from report protocol, some HIDs support also boot protocol, which is a much simplified version of reporting data. And as you can already guess, keyboards do support boot protocols, and boot protocol is also used in this project. After the short introduction into the USB, let's have a look at the project itself. The aim of the project was first to design and implement a low-speed USB host in GA144, then to implement a keyboard controller so that we could plug a USB keyboard into Greenery's eval board and use it to enter correctures. Finally, I will demonstrate usability of this controller in an Etherforce editor. Before we dive into details of the USB host implementation, we need to show how the specification has been simplified for this particular project. On the hardware side, we didn't employ any control of rise and fall times, and there's no root hub nor support for hubs. This may seem strange, as without hubs only one device can be connected to the host. However, for this project we don't need to connect anything else than just one keyboard, so the simplification is acceptable. Regarding protocol, it has been proven that with only one device attached to the host, there's no need for assigning an address to the device, and zero address can be used all the time. Also, we never transfer more than 8 bytes of data in a single transaction. Thus, data 0 and data 1 toggling is not checked. We also disregard stall handshake. Finally, the keyboard controller does not provide for auto-repeat feature, and it also ignores simultaneously pressed keys except for Shift key. Let's have a look now at hardware part of the project. Hardware is really simple. We just need a voltage level shifter since GA144 runs at 1.8 volts, while USB signals are 3.3 volts. The best option seems to be 74LVC 2T45 chip. The resistor at the direction input is there because we control this input with an analog output pin of GA144, so we need a load resistor. Unfortunately, we could not use level shifter TXB0108 available on the eval board that can switch direction automatically, nor its open collector version TXS0108. None of them worked well with USB pull-down and pull-up resistors. We also have a USB Type-A socket with two 15K pull-down resistors soldered directly on the eval board. And that's all hardware we needed. The setup of this project then includes a USB keyboard, the voltage level shifter just shown, an eval board, and a PC with ArrayForce IED. Now we start examining the software part of the project. First, let's see the floor plan. The USB host is implemented in 18 nodes of the host chip. The serial interface engine consists of 11 nodes, and the keyboard controller is made up of 7 nodes. The serial interface engine consists of a clock module, 2 transceiver nodes, a transmit path, and a receive path. The keyboard controller consists of a module with description of packets and transactions, the controller itself, and a character decoder. For the purpose of demo application, we also have a link that allows communication between the USB host and ArrayForce IED. One important note about data and commands. As was recently discussed on SVFIG forum, it has become a de facto standard to treat data in multiples of 8 bits. Thus, we usually have 8, 16, 32 and even 64-bit words. One advantage of GA144 chip is its unconventional 18-bit word. In such a word, we can have, for instance, 16-bit data write justified. This gives us 2 extra bits that can be used as a kind of supplementary information embedded in data or simply a flag. We can have a stream of bytes or 16-bit words with top 2 bits cleared. This would be our data. However, when bit 17 is set, we know the information in the lower 16 bits is not data but something else. For instance, an address of code to be executed. We can jump to this address with push return instructions, or we can call this address with push X instructions because only low 10 bits are placed into the instruction pointer and the rest is ignored. This feature is widely used in our code. So whenever we say data, we mean a word with its most significant bit low, and when we say command or message, we mean a word with its most significant bit high. Now we'll see how the USB host is implemented. We'll start with a serial interface engine. First, there's a clock module. It's composed of 3 nodes: an oscillator with 12 MHz ceramic resonator on its GPIO pin. The oscillator provides a double frequency signal to node 317 with a period of 42 nanoseconds. At low speed rate, it represents 16 clock periods per bit. Then we have a wire node passing this signal to a timer that provides millisecond pulses to node 216. Next, we'll have a look at transceivers. Transceivers are implemented in nodes 317 and 217. Their GPIO pins are connected to D+ and D- lines. They receive 24 MHz clock to up port of node 317. The node itself is controlled via its down port. When transmitting, node 217 is controlled via its write port, while when receiving, it's controlled via its up port. Both GPIO pins are initialized in weak pull-down mode. The pin in node 217 is also used to detect low-speed device attachment. Based on desired activity, we have to switch direction of the voltage level shifter. To this end, we use node 117 and its analog output pin. When we want to get data from a device, we call word in to set direction line low, and when we send data to a device, we call word out, which sets direction line high. Let's see how transceivers work in transmit mode. There's word bit in node 317. This word contains 4 micronext loop that fetches 16 times from up port. This takes 16 clock periods, which is length of 1 bit. Then we jump back to down port. Next, we have 2 words controlling state of D+ line. Plus J sets the line low, while plus K sets it high. Notice that both words end with call to bit, which separates 2 consecutive calls by exactly 1 bit time. This creates the basic transmit timing mechanism. In node 217, there are similar words J and K. Executing J, we first call plus J in node 317, which sets D+ line low, and at the same time we set D- line high. Then we set out direction of the bus. Word K works in a similar way, as well as word single-ended 0. Finally, we have word idle, which calls idle in node 317, and both set GPIO pins in weak pull-down mode. Then we set in direction of the bus. Here we have an example of waveform generated by the transmitter. We can see a start of frame signal, 1 bit K state, 1 bit J state, and end of bucket signal composed of 2 single-ended 0 states followed by 1 J state. At the end of J state, we can distinguish beginning of idle state. Now we'll turn our attention to transmit path. Transmit path is composed of three nodes: serializer and CRC calculator, bit stuffing, and encoder. The path receives a stream of bytes via write port of node 115 and outputs corresponding J and K states via write port of node 216. Commands that control the transmit path are intertwined in the data stream. We'll follow the transmit path from the encoder backwards. Encoder node receives a stream of bits and converts it into J and K states by calling appropriate code in transceiver node 217. The code for encoder is given here. Definitions begin with a variable state, which holds value of the last transmitted state, 0 for J and 1 for K. The execution starts in word transmit. It is an endless loop where we fetch a word from up port, and if the word is a command, we call the appropriate code with push X instructions. Upon returning from called word, we jump back to transmit. If the fetched word is data, we call the word encode to convert the bit into appropriate state, and then jump back to transmit. Word encode compares the bit on stack with the value stored in variable state and calls either K or J in node 217. In either case, we store the transmitted state in the variable state. Other words in this node are commands. We have the end of packet command, keep alive command, which waits for a signal from a 1 millisecond timer in node 316 and then sends the end of packet. Command start of frame is called right before a new transaction begins. It is similar to keep alive command, but it also tests if the device is still attached. A command executed for a newly attached device is reset. It generates a reset state of the bus. We also have rx command, which hands over the control of transceivers to node 117 when we want to receive packet from the device. Bit stuffing is carried out in node 116. It passes all data and commands from left port to up port. Bit stuffing algorithm is simple. Let's say that this is a stream of bits passing through the node. When it encounters 6 consecutive 1 bits, it just inserts a 0 bit into the stream. The first node in transmit path is serializer and CRC calculator. It performs several simple functions. It serializes all data bytes, least significant bit first. It calculates CRC for all data bytes, and it passes all commands except for two intended for this node. One is clearing CRC register, and the other sends 16-bit of CRC out for transmission. We'll have a look at transceivers again, but now we'll see how they work in receive mode. The most challenging problem in receive mode is how to synchronize receiver's clock to incoming data. A solution to this problem is a self-synchronizing clock. The algorithm is first explained graphically. Assume this is a time axis with marked 16t intervals. This would be a signal on D+ line. The arrow indicates that we start from idle state. The algorithm starts waiting for a rising edge. When it arrives, we start counting 8t interval to get to the midpoint of this bit. Here we read state of D+ line. From now on, we start counting at most 16t interval, while at the same time we look for a falling edge of the signal. When the edge arrives, we stop counting and start 8t interval again. At its end, we detect and record state of the line. The algorithm repeats. We count at most 16t while waiting for an edge, and so on. A different situation arises when there is no edge detected within 16t interval. In that case, we read state of D+ line at the end of the interval and start a new 16t interval waiting for an edge. So the algorithm can be described in several steps. Detect an edge at the beginning of a packet. It is presumably the first edge of sync pattern. Count 8t interval and read state of D plus line. Count up to 16t while waiting for an edge, and if detected, stop counting and go to step 2. Else, if edge not detected within 16t interval, read state of D plus line and go to step 3. Thus the clock is resynchronized at each edge, and due to bit stuffing, we resynchronize at most after 6 bits. Now we'll see code of the self-synchronizing clock. First, we'll examine code in node 317. Here we have word fetch bit, which waits for 8t, then reads state of D plus line and jumps to down port. Notice that the state of line is not sent anywhere. It stays on the node's stack. However, we can get this value by reading stack content with code executed in down port. Thus, wherever word fetch bit is used, the execution stops and continues after node 217 sends store to P return instruction word to down port. This code sends top stack item of node 317 to node 217 and execution resumes where word fetch bit has been called. Next word is edge. This word is essentially for next loop. In each cycle we wait for 1t and then read state of D plus line. If the line is high, we've detected a rising edge of sync pattern, so we discard the loop index and return. The loop runs for at most 17 bits time. If no edge is detected within that time, we leave a 0 flag on stack to signalize timeout and go to down port. Word sync first calls edge. We now see that if the edge on D plus line hasn't been detected, we jump to down port and never return back to word sync. However, if edge has been detected, we return here and execute fetch bit, which leaves non-zero value on stack. After node 217 reads the flag, we continue from sync by following through to word isJ. IsJ is a for next loop of 16 cycles. In each cycle we wait for 1t and read state of D plus line. Then we test if the line is low. If so, we've detected an edge of J state, so we wait for 8t interval in fetch bit, read D plus line state and leave it on stack. When read by node 217, we jump to word isK. If no edge is detected within 16t time, we jump to down port, so that node 217 can read the last state of D plus line left on stack by fetch B instruction, and finally we jump back to word isJ because we still wait for J state and its leading edge. Word isK works in the same fashion. Both isJ and isK are the heart of the self-synchronizing clock algorithm. As long as node 217 reads D plus line state values from stack, the algorithm is running between these two words. Since for each bit we jump to down port, we give node 217 control of this algorithm and an opportunity to stop it by jumping to any other word in node 317. Code for receive mode in node 217 starts when node 216 calls word hand that informs node 117 that we will receive a packet from a device and hands over its control by jumping to up port. Word read is the one that sends instruction word store to P return to node 317 to get its top stack item and leave it on stack here. The main code for receive mode is in words next and input. Word input first calls sync in node 317 and reads a flag. If it is non-zero, we've detected an edge, so we send this information downstream and keep the state of D plus line here on stack. Then we read state of D minus line and send state of both lines to node 117 for further processing. We finish word input by jumping to up port. If, on the other hand, the flag from calling sync is a 0, we send it downstream as an error flag and then jump to write port because this is the end of receiving data from a device and we are getting ready to transmit again. Word next reads D plus line state from node 317 and jumps ahead in order to read D minus line state and send both values downstream. It then also jumps to up port waiting for further instructions from node 117. This picture demonstrates where individual bits have been detected. We can see some variations, but on average state of a line is always detected in the vicinity of a bit center. Thus the algorithm works as expected. Now we'll go quickly through the receive path. It is composed of decoder, bit stripping node, and deserializer and CRC calculator. Receive path starts reception of a packet and checks for possible timeout. It then receives a stream of D plus and D minus line states and outputs decoded bytes. It also informs controller about the device being attached or detached. And as already mentioned, it switches direction of voltage level shifter. Let's have a look at the decoder's code. Here we have a variable D minus holding the last state of D minus line. Then we need a word that converts D minus line state into bit value. In this word, we compare current D minus line state with the variable D minus. If changed, the bit is 0, else it's 1. We use number 80 hex for 1 bit because serial data are received least significant bit first, but this serializer assembles bytes using right shifts, so we have to start from bit 7. The main word for receiving packets is Rx, which is called when we expect a packet from the device. It initializes variable D- to idle state of D- line, and then it calls word input in node 217 and fetches back a flag. If non-zero, we have a sync recognized, and we jump to word receive. Here we receive a pair of D- and D+ line states. For each pair fetched, we test end of packet signal, which is recognized as both lines being low. If it's not end of packet, we call word bit, send the decoded bit downstream, update variable D-, and call word next in node 217 to read the next bit. Then we jump back to the beginning of word receive. Thus we receive and decode all bits until we get end of packet signal, which is reported downstream, and execution continues towards TX, which does some housekeeping and returns control of node 216 to transmit path. Then we jump back to up port. In case there is a timeout reported from node 216, we pass that error to a controller and jump to up port. Bit stripping works in the same way as bit stuffing. After 6 consecutive 1 bits, the following bit, presumably 0, is removed from the stream. The serializer converts serial bit stream into bytes. It starts CRC calculation for data packets and checks CRC when whole data packet is received. Handshake packets and messages are passed without CRC calculation. And that's all what makes a serial interface engine. We have seen how bytes and commands are sent through the engine to a device, how the engine controls all the traffic over the bus, and how replies from the device are converted back to bytes and messages. We've also seen the delicate interplay of transceiver nodes with encoder and decoder nodes. We've seen how they pass data and control from one to the other, how they execute each other's code with port execution mechanism, and so on. An important point is that this serial interface engine can be used to communicate with any low-speed USB device with no modification whatsoever. We use it here to control a USB keyboard, but we could as well use it for mouse or a joystick. The difference is made by packets sent to the particular device and received back from the device. And those are assembled and analyzed by a controller that is specific for each kind of device. Thus, to control a keyboard, we need a keyboard controller, and this will be presented now. Since keyboard controller code is less general, in the following I'll show only the most important features. First, we'll see how packets and transactions are predefined. All packets we need are stored in node 215 in a compact form. There's only data, no code. Each packet starts with length of record, and other words contain bytes, pairs of bytes, 16-bit numbers, or commands making up the packet. For instance, setup packet is composed of a sync byte, setup PID, a word with address 0, endpoint 0, and CRC5 checksum. The last word is a command for node 214 to execute word stop. Node 214 is responsible for extracting individual bytes from compressed packets. There are also definitions of commands, which are sequences of actions that are used in multiple packets. When we encounter a command in a packet description, we call its address with pushx instructions. In case of setup packet, we execute word stop, which contains a command for serializer and CRC calculator in a node 115 to execute from its write port. Then we send a call to word clear, which clears CRC calculator. And finally, we send a command to encoder in a node 216 to generate end of packet. Another example is conf data packet. It is sent to a device to set configuration. It is composed of a sync byte, data PID, a command to clear CRC calculator, then there are 8 bytes of payload, and finally a command CRC fetch. This is again a word in node 214 which requests the CRC calculator to send 16 CRC bits out. Then there's a command for encoder to generate end of packet. And finally, we execute another command in encoder word rx which sets transceivers into receive mode because we expect a handshake packet from the device. Node 114 combines different packets into transactions. For instance, the set configuration transaction we've just seen is defined as two packets named setup and conf that are compiled in node 214 at those addresses. Thus, calling word set configuration in this node carries out all actions related to this transaction. We defined here also several simple actions such as reset command for encoder node 216. In the very heart of this module there are two controller nodes. During initialization, node 15 is a master and node 14 functions as a wire between node 15 and node 114. Code in this node defines a sequence of transactions taking place during initialization of a newly attached keyboard. We start by calling word reset we've seen in node 114. Then we configure the keyboard. The first transaction sets keyboard's configuration. Word request calls word set configuration in node 114, and word status waits for a handshake packet to check if the transaction has been successful. If not, the request is repeated. If acknowledged as successful, we continue with the next request. After last configuration request, which turns on the caps lock LED, calling word keys in node 14 transfers control to this node, and node 15 jumps to write port and becomes a slave. The main task of node 14 is to request and process reports. Most of code is dedicated to that task. We'll just look at word keys, which is an endless loop. It repeatedly calls word wait in node 114, which sends 50 keep alive signals. Therefore, we wait for 50 milliseconds, and then we issue an in transaction from endpoint 1. This is the endpoint that sends a report on currently pressed keys. Then we call word report to process received data bytes. Report is an 8-byte data structure shown here, where modifier keys are encoded as a bit array. Node 14 ignores all reports except for those with only one key code reported, so we ignore multiple keys pressed at the same time. We also process only shift modifier keys. Only those 2 bytes are sent out for character decoding. This takes place in character decoder module. The decoder occupies node 13 and 12. It receives key codes and sends them out converted according to chosen character set. A part of key codes provided by a USB keyboard is shown here. For the purpose of demo applications, we've chosen to convert key codes into Ether4th character set. To this end we use two methods. First, we subtract a constant from key codes to remove error codes. Then we can identify a block of letters that can be converted to Etherforce characters by adding a constant. There are also two other blocks, non-printable characters and function keys, which can be processed in the same way. Finally, we ignore non-alphanumeric characters not present in the Etherforce character set. What rests is a small set that we can store in a hash table. The table looks like this. Each word in the table contains a key code in the low 6 bits, which is used as an index. Non-shifted and shifted characters are then stored in middle and top 6 bits respectively. Function keys and non-printable characters have no code in Etherforce character set. They can be encoded either as messages with bit 17 set, or they can be converted into call instructions that we can send directly to a target node for port execution. And now is the right time to demonstrate how the USB host and keyboard controller work. In this demo, I'll show how a keyboard can be attached to and detached from the eval board and how keys are processed. We will use the ArrayForce IDE to inspect stack content of node 11. This node receives characters from the keyboard controller and places them on its stack. When I plug the keyboard into the USB socket on the eval board, you may see all keyboard LEDs blink, which indicates that the keyboard has been reset. And now only caps lock LED is on, which is indication that the keyboard has been initialized properly and is ready. When I start typing, you can see Etherforce character codes appear on stack. First, typing letters from A to H, then numerals from 0 to 5. Now, if I detach the keyboard and attach it again, the controller detects the keyboard, resets it, and configures as indicated by caps lock LED being on. I can now continue typing as before, several more letters and numerals. When I press keys with non-printable characters, for instance space, enter and escape, you can see call instructions instead of character codes. Function keys are encoded as messages with bit 17 set, with the low bits corresponding to the number of the function key F1, F2, F3. It demonstrates that the host takes care of this newly attached keyboard and Node 11 does not need to be aware of what has happened. It just shows characters as they are received. In the next demonstration, I'll show the current state of Etherforce. 8 years ago, Chuck Moore presented his character-oriented display generated by Evalboard, which was part of the Etherforce system. At that time, I hadn't had any experience with Green Array's chips yet, but his presentation may have been the spark that ignited my interest in those chips. 2 years later, I started my collaboration with Green Arrays, and then I became also interested in Etherforce. When Chuck's website colorforce.com was still running, there was some information about Etherforce in his eval weblog. The site is not on anymore, but the content is archived on GitHub. As it seemed that Chuck had put aside Etherforce development, I asked him if he would share the code with me, and I'm very grateful he agreed. So the work you'll see in a few moments is kind of continuation of Chuck's original development environment. So what is Etherforce? From the Chuck's eval weblog, we learned that Etherforce is a variant of ColorForce that resides on Green Array's multi-computer chips. The ether is then a term for software in every computer's RAM that routes messages about the chip. It is actually similar to Green Array's ganglia. As with ColorForce, tags are used to identify pre-parsed words in source code. In contrast to classic ColorForce Shannon-coded characters, Etherforce uses 6-bit characters preceded by a 6-bit tag. It also uses 6-bit tokens to indicate F18 instructions. There are already some modifications made to tags and tokens assignments, so this table is slightly different from the original. The table shows that the tags have two most significant bits set high. Tags define in what color the following word should be displayed. Some tags, such as space and end of block, have no color. Tags also define how to interpret the following characters. They may represent, for instance, a decimal number or a word. Color then indicates whether such a number or word should be interpreted or compiled in the same way as in colorforth. The first two tags signalize tokens. Tokens are 6-bit characters that are displayed as character strings. First 32 tokens are reserved for F18 instructions. Then there are 16 other tokens for names of ports, registers, or program flow control words. To make the encoding scheme clear, I'll show a short example. These are two lines of source code that would appear on display. Now we'll show a part of display buffer where each rectangle represents one 18-bit word, which is divided into three 6-bit characters. The text on display is gray, and we apply corresponding colors as we fill the buffer with tags and characters. We start with red word move. The first item in memory is 35 hex, the tag for red words. Then 4 letters of the word move follow. Then we add a green decimal number 7. Again, we have a tag and character added to the buffer. Now we enter several F18 instructions, which are stored as tokens. The entry starts with 31 hex, a tag for green tokens, then follows one token per character. By now, you could have noticed that each tag is displayed as a space in front of the word that follows. However, when we print tokens, there is a space in front of each of them. The line ends with end-of-line tag. When display code recognizes this tag, it prints a space, as for any other tag, and then adds a blue comma so that I can see where the line ends. We move to the next source line on the display, but we simply continue filling the display buffer, now with a red word Go. We add a hexadecimal number 20, and 3 tokens follow. Notice that word left is not an F18 instruction, but it is convenient to have it as a token too, so it occupies only one 6-bit character in the buffer. Although green word move has the same color as preceding F18 instructions, we have to encode it with its own tag as a string of green characters. And since semicolon represents return instruction, it has to be encoded as a green token. Finally, we add the end of line tag, and if this is the last line in the display buffer, there's always an end of block tag. In the two lines of source we have 51 characters, including spaces between words. To store this text in the display buffer, we used only 11 words. This is 33 6-bit characters. This shows that the encoding scheme designed by Chuck is really very space efficient. Back to Etherforce. It was supposed to become a standalone operating system that boots from Flash. It would expect external RAM memory, an RGB video monitor, and 4-key keypad. Now, the keypad is the only thing that I didn't really like, and that was the real motivation to develop the USB host and keyboard controller. Other than that, Etherforce is still a system I'm very enthusiastic about. So, how Etherforce looks like today. This is the current floor plan of Etherforce. In this part is Chuck's display code with some minor modifications. It renders one block of source code on a VGA screen. Its resolution is 24 lines of 50 characters each. Here we have a SRAM controller with an arrow indicating how source blocks are loaded into SRAM from a PC with the help of Ether. In the future, it will be loaded from either onboard flash memory or from an MMC card. Here is the USB host and keyboard controller, and this part generates horizontal and vertical sync signals as well as character clock, which is fed into node 715 internally, so we don't need any external wire. It uses the USB oscillator as its clock source. And the last part is an editor, which I am going to show in action now. First, we load Etherforce code from PC. This intro screen shows the system is running, and now the first source block is displayed. The editor has two modes. First is navigation, which allows to move between blocks, move cursor by lines down and up, and to move by words right and left. The editor uses the same keys for navigation as colorforth. The second editor mode is used when we want to type a text. It is invoked by one of 12 function keys. Each key represents one tag, so that when we enter the typing mode, we also choose what color the text will have. Let's move to the next block and add some new definitions right below this line with comment. The definition starts with function key F8, which starts red words. When we type the name, we switch to green decimals with F2, enter the number 7, and switch to green tokens with F6. Now, typing tokens requires some training, as each token is entered as a single key press. The current keyboard layout, including tokens, is shown here. Entering F18 instructions this way is kind of similar to entering basic keywords in some home 8-bit computers, for example Sinclair ZX Spectrum. The end of line is simply generated with Enter key. Then we can continue the next line. Again, we switch to red words, type a name, then key F4 turns green hex numbers on, F6 turns back to green tokens, then we use F9 to turn to green words, so we can type word move. If we make a mistake while still entering characters, we can use backspace key to correct the word just being typed. To enter this word and move the cursor forward, we either change color with the function key, or we use spacebar if we want to continue entering words of the same color. Finally, we enter semicolon as a green token, and that's all. End of block is always present at the end of source block, so we don't need to enter it explicitly. To leave the typing mode, we just hit escape key. The editor also allows entering spaces similar to blue dots in colorforth. These are entered with a tab key. The changes made to the source are automatically stored in SRAM during typing, so that when we leave the typing mode and move to another block and back, the changes we've made remain. Since the editor is still being developed, some functions, such as deleting whole words or copying words and inserting them elsewhere, are still waiting to be implemented, as well as other parts of Etherforce, such as some minimal interpreter and, of course, compiler. And we are almost at the end of my presentation. By now, you should know the answer to the question asked at the beginning. Hopefully, it has been sufficiently demonstrated that green erase chips can speak USB, even though slowly and with only one interlocutor at a time. I wish to thank Green Erase, namely Greg Bailey for his support and friendship, and Chuck Moore for giving me his Etherforce source. I'd like to also acknowledge MQP Electronics, a UK-based company, which owns rights to the tutorial USB Made Simple and which allowed me to use it in this presentation. Thank you for listening.